So thank you, Karen, for that beautiful introduction. So clearly you are the poor souls that care about profiling. Everybody else has their performance problem solved, I see. So you are part of a small but select group of fellow software. So anyway, so as Karen said, my name is Gabriel Esteves. I work for Intel on-site at Microsoft. And for the past year or so, mostly on machine learning and inference, the deep learning inference, sort of part of the loop. So that has colored some of the stuff that I'm going to be talking about. So hopefully it's of some value to you. So the way that I like to go about this talk is, well, first tell you, okay, so exactly what kind of profiling, because there are very many kinds, and it's a very big word for a lot of different aspects of the problem. Then go over some general observations about the how to solve performance problems. Then specific solutions that the PyData and the numerical Python and Intel optimizations has done, and finally just basically go over it and like hammer the point home, hopefully. So Python, as I'm sure I don't have to convince you about, it's a very expressive language. It is pretty much like the de facto language for machine learning and scientific computing. It's very good at getting rid of the incidentals of an application and a problem domain, but it is not fast. So or at least it's not the fastest language around. But it abundantly makes off for the productivity and developer notions that it brings up. So not only on the Python language itself, but in the ecosystem of libraries that has accrued around it. So the position that my employer takes that I believe is a valuable one is, let's not change things. Let's just try and take Python as is, take the libraries as they are, and try to make that a constraint. What can we do to make this stack run faster? And the stack that I'm talking about in particular is one that looks like this. So you have Python that essentially you use to specify a high-level description of your problem and hopefully your solution in terms of lower-level abstraction. So now you're not talking about sentiment analysis, but you're talking about matrix decomposition. You're not talking about recognizing one's face, but you're talking in terms of, I'm using this deep learning model to do it for. But once you've done that, you don't necessarily want to clutter that description that may be complicated enough with the details of how to make best use of the hardware you're running in. And that's where a rich ecosystem of native libraries have come in. And here I have a sampling of some of those libraries, and you see prominently featured are NumPy and scikit-learn that now is I think it's 27. So it's past their 10-year anniversary. TensorFlow, PyTorch, and here I have this that it's considerably less well known. It's the Onyx runtime, which is the particular layer that I'm working on, which is an inference runtime from Microsoft. So again, your solution will look like a Python code that under the hood calls a bunch of C++ code that decides then how to best use the hardware. And then you will deploy this in a variety of circumstances. Here I have, how will you deploy it as a service on the cloud, but that also looks like you will deploy it to a heavy edge, a gateway just to put it close to where you're getting data from your sensors, or ideally even to the lower constrained memory devices that have very specific SLAs and even real-time processing requirements. So that's kind of where the wheels come off the wagon when you have all this beautiful data science work, all this work that you've put on the statistical side of things and solving a problem. Turns out that even though in development, when you have a cloud that with basically infinite resources, it works beautifully, it turns out that it's not good enough because the hard reality of hardware comes in and says, I cannot run this. Or I cannot run this, but come back next week. And that's kind of like the kind of deployment that I'm trying to illustrate over here. The other one is one that I see more and more, where Python is kind of an embedded component in an application. So things like Blender, things like Unity and game engines they can be scriptable through Python. So then this stack has a layer on top of it, where is the host application. So you have Unity or Blender calling into Python that then calls into C++ code. So things become baroque. So anyway, but the whole idea of illustrating this is that if you can improve the running time of this particular piece of the stack, you are benefiting a number of deployments and a number of scenarios. So, and the way you go about this is no surprise to anyone. This is pretty much how the process looks like. You first make sure that the thing runs and that it runs, that you're getting the right results, because there is really no point in generating zeros really, really fast. So then once you have some clarity, and this is where unit test comes in. So you make sure that you're getting the correct results. After anything before that doesn't matter. So when you're sure that your application runs, you're getting correct results, then you measure it. Say, okay, how long is this thing taking? Then determine, and this is a very utilitarian view of things. You don't go after what you know how to change, but you go after the stuff that's taking the most time. There are clear bottlenecks you're going to see in your application, and the obvious way is to go after them, because it doesn't matter what other improvements you make; those are the ones that are holding you back. So you implement the changes that address those bottlenecks, and you go at it again. So the specific version of this loop that I have in mind that I'm going to be addressing in what remains of the talk is a very interactive variation of that. When you actually have the code in front of you and you are going over this loop, and you get immediate profile or immediate-ish results. But you can do this offline. So where you actually distribute your Python kernel or a bunch of machines, and then just after a while you get a profiling trace. So it's less interactive. The work still the loop still works. It's just not continuous, right? Like it's not as iterative as I will make it sound. And one thing that's very important, and the Vikram's talk I kind of alluded to this, is as part of the functional. Once you design, this is an experimental design problem. So you have part of your functional testing must include what part of the stack you're actually testing. Once you get performance results, it's very important to know that you're not actually testing, you're not profiling the tests. When you get like a very weird, unexpected performance results, you have to make sure what part is causing the problem, whether your actual stack or your workload. So you need to be like, all of this is an art, and it requires a human in the loop. So any company that comes to you and says, I've solved this problem and here is the box that does it, please take it with a grain of salt. So we're not that company. So anyway, so the way that we've proposed to implement this loop is essentially you take your stack, and then you use Visual Studio Code, but you can use any kind of ID, And we have interposed a component that talks to a profiler, something that will measure the use your code is making of the computational resources you have at your disposal. In particular, the profiler we're talking to is Vitune, which is the one profiler that knows the most about Intel hardware. But you can imagine connecting things like cprofile, which is the standard profile in Python. The good thing, or the kind of the party trick that Vitune has for Python workloads, is that it's a mixed mode profiler. So it will give you the Python stack and it will stitch the C++ stack together. So most Python profilers, maybe the vast majority of Python profilers, will stop for anything that reaches this edge is a black box. So it'll tell you matrix multiplication takes a long time, and then you'll say thank you, but now what? So it's more useful to say, okay, matrix multiplication in particular, or like say image decoding is taking a long time, and then you say, okay, so what part of image decoding? Or if it's only when I'm dealing with JPEGs, if that's the case, then you can probably replace that library or recompile the library to take advantage of the capabilities of your hardware to run that part faster. So anyway, and this is kind of some of the actions that we can recommend to accelerate the code. So either change your Python code, make use of like the many fine alternatives in concurrency that are out there, multiprocessing, async. Those are all fabulous ways to, and that make it, if not very easy, at least it make it fairly straightforward to rewrite your code. But not all problems lend themselves to being parallelized or being broken up in ways that you can take advantage of this. Even it doesn't matter how easy it is to write if they don't apply to your problem. Some general things that you can do that usually make things better, maybe not so much better, is try and write code that looks more Pythonic. So use like map, use filter. Don't try not to use as many for loops. But all of that is kind of saying like brush your teeth, right? I mean, yeah, it's good. Maybe it will help in the long run. Maybe they won't be addressing themselves to the bottleneck that you may be having. So. And then the battle axe of performance recommendations, don't use Python. So change that part of your code that's taking the longest time to some native library. And for this, there are many options you can do. Python, you can do things that look like Python, generate better code, and we won't require of you to port your whole code base, because then you have only shifted your problem. Now, your problem is not a performance optimization problem, your problem is a rewrite problem, and your management may not be all that open to the solution, to call it, somehow. But let's say that you're tight, you have a hard constraint on the libraries that you're using. You can still do things that will improve your code without having to change the stack all that much. So you can recompile your dependencies with alternative compiler flags that address themselves to the functions that are causing you problems. So and things like conda build and scipy build projects are making that increasingly easier. Still not something that you would tell an intern to say go off and do without their getting some trepidation. So what we are one of the solutions that this group at Intel has determined that it's most appealing to people is we will present you performant libraries optimized for the hardware that look exactly like some of the components that you may be using already. And we've called this the Intel distribution for Python. So you don't need to, so don't let the name, make you believe that, okay, now I have to, you're asking me to replace my whole stack. So you can do this piecemeal. You can say conda, and from this conda install from the channel Intel, get NumPy. You don't have to replace all your Python innards from the top to bottom. You can just choose what libraries you take from that channel of deployment and try it. If it works, if some of them may solve the very problem that you have, some of them may not do so well, so you will have to iterate over this. And the way that you iterate over this is it's what I'd like to show you. So so here I have Visual Studio Code, and it has a very simple PCA, the composition problem. PCA is a very common feature extraction technique. So it's, again, nothing too onerous. And if Visual Studio allows me to do this, I will like to show you how. So the idea here is that you just say Python start debugging, and it will kick off a version of, instance of vtune. That's the profiler that I talked to you about before. It goes off, takes a lot of time that I will now try to fill in with random talks. But anyway, you're not missing anything going on the screen. This is what will happen if you are using C profile or any other profiler. So essentially, what this is doing is running your application and gathering a lot of data that. And this is not limited to, of course, to Intel hardware. Many hardware vendors have a built-in, we call them performance counters, which is a specialized hardware that allows you to determine how well the rest of the hardware stack is being used. So and that's probably one of the problems. So to use, typically you don't come across performance optimization problems when you have tons and tons of time in your project. Usually you come across the problem when you're really dead set against a deadline. So you don't want to learn how to use a profiler in anger. There you get a ton of information that now you have to learn how to use, and because you don't have enough lots of time, this is kind of what we're trying to. We're trying to give you a idea of what things. Best level information, not suggesting is the only one that's useful. So here I've used the vanilla scikit-learn stack to collect data on this kernel, and it tells me, okay, so most of your stuff happens all over the place. So see, this is a module breakdown. Module is basically the libraries that each that's presented in particular. MKL is one of the modules that NumPy makes use of to do matrix stuff. So here you see that, okay, so this stuff is basically NumPy doing its thing. And it takes 22 seconds. Fair enough, okay, so but with this particular Intel library that's called dial4py, which is an interface to SciPy that it presents some optimizations to Python. I'm going to uncomment this call that uses monkey patching, so your code remains as is, and all you have to do is profile again, and it goes through the same song and dance. It takes the same amount of time, and then it lets me drone over it for a while. So it does its thing. It took less time, and it will come back eventually and hopefully tell me that it took less time. So now I run out of things to say. So okay, so here you see, okay, now it took 3 seconds, which is good. And the way that the module distribution is shifted is that now all the numerical stuff that was being carried to NumPy now was performed fast enough that it doesn't really show up in your bottlenecks. So that's good. Now it means that if this is good enough, now you're happy, you send to production. If it's not, then rinse and repeat, right? So this is kind of a job security sort of deal for performance engineers. Okay, so this can be done. This sort of loop, as you can imagine, can be done in any IDE and presented in many ways. Vision itself has its own standalone, but Visual Studio, in particular Visual Studio Code, is very. It has a bunch of things that make it unique and attractive for this sort of work. In particular, it breaks down the services that usually lived inside a package inside Visual Studio. Now they are all exposed as services that can run in different parts. In particular, they have this language server protocol that allows you to do all what the language services do. Essentially, gives you a view of what the Python actually, so the code actually looks like. That we are now trying to marry with the profiling data that we are seeing, so that we can show you not only what functions are being used, but what lines of code incur in what cost. So I'm not saying that it will be very useful to see, okay, I'm going to give you the disassembly, and that this particular line of Python generates this disassembly. This may be useful for some cases. Our position is that for a data scientist whose job is to make this run fast, may be less useful. So the idea is just give me the data at the level that it's useful to me and that allows me to make a decision. And so anyway, this is the stuff that I've talked to you about. All of it, except the VSCode integration, is available now. I had the references. The references are here. I encourage you to use them, but I would be very, very interested in having your feedback on the Visual Studio Code integration, which is my project, which is what I'm trying to get whether people care about or would find useful. So if you'd drop me a line to my email was at the beginning, or care to talk to me after this talk, I'd love to hear more. I mean, if the determination is I would never ever use it, that's useful for me as well. Less hurtful, but useful. Anyway, so for this, so what if there's nothing else, what I'd like for you guys to remember from this talk is that the way that you deploy things, the way that Python allows you to deploy things, is very amenable to optimization. So the next time that you hear that somebody tells you, "Oh, Python is slow," sometimes it's true, but in many cases, it's not so much Python, but the way that they're using it. So it's worth to take a look to find out optimization opportunities in those particular deployments. And it may end up that, okay, yeah, you need to change, you need to use something else, but not just out of reputation, just discard those opportunities out of the way. We believe that some of those opportunities can be found by having a very, very tight integration using the IDE, but it's not the only way. And please give the optimized. If your hardware, the hardware you're deploying on, is Intel hardware, it doesn't need to be only CPUs, but like integrated GPUs. Please give these libraries a try and let us know how do they work for you. So that's my talk down. Thank you so much.
That was really fun. I don't think of VS Code as being a profiling tool, so that was really exciting.
Yes.
To have that and be part of that experience in a different way, that's really useful. So great talk, obviously, and we have time for some questions. Do we have any questions in the room?
Great talk.
Thank you.
I usually don't look at profiling as, hey, which library is my troublemaker? I usually look at, hey, which function call, which line, which half of the line, which stupid thing did I do with a dictionary is my troublemaker? Do you want to show the breakdown? Yeah, I figured it was probably the next scroll down.
And this is not a breakdown that you would find useful in this particular line of work, because I purposely make this workload go all the way into native, so it wouldn't help you all that much. But if it had spent more time on Python, you'd see the actual breakdown into the calls that the interpreter made. And then if like you say, like, oh, this may be a problem with a dictionary, or is it like is the dictionary too big, or is my service taking too long? Those are the things that you discover here. Something else that the Microsoft stack has, and the Microsoft guys are working on, that I think would benefit very much of this, is they are putting a lot of the code, like the symbol information, the debugging information that's normally used for debugging purposes, online on GitHub in such a way that you can actually, so here you see a bunch of funcs that, like, some functions that are not useful to you at all. They are not useful to me at all either, because I didn't install symbols on this particular machine. They wouldn't even probably be useful even if you had symbols, because you say, okay, this is code that God knows where it came from. So Microsoft is now pushing for this source link, not technology, but it's just basically a different way of putting symbol information that is tied up to a particular GitHub repo, GitHub commit. So you would see if your problems are still in the native libraries, you could go to the particular tag from which the library that you're now using was cut from. So you would get the actual source that is causing you problems. And then and the important thing is not so much what you can do with it, but you can actually see, because it goes to GitHub, you can see, okay, so maybe people have talked about this. Maybe there's an issue about it. So now this is part of, like, like becoming, and I guess building this sort of community is important for. So that's, you have, instead of go over Stack Overflow and saying, have you guys seen this? You actually have people who are addressed to that part, maybe your particular problem in the code as it is. But then again, this is my hope rather than something that I can offer you tooling for right now.
So recently we have also started using GPUs for running part of our code. So is the profiler also capable of, like, figuring out what's the runtime of a function on a GPU within the same context?
Yes, it is, and GPUs. So this profiler is capable of profiling a GPU as long as you're using it using OpenCL. So if you're using CUDA, we cannot help you. But not because we don't want to, mostly because we don't want to, but also because the GPUs that Intel offers now, the integrated GPUs that Intel offers now, and things that we plan on offering in the future, not only limited to GPUs but to FPGAs, use OpenCL. So you can use NVIDIA cards using OpenCL, and then this particular profiler will be of use to you. But NVIDIA offers its own tooling that could very well be connected to the architecture that I showed you before. So my hope is that I can put this in the open source and have people that want to offer a similar view of their hardware. So kind of build what the language service protocol is for language services for profiling and tracing information. I hope that answers you.
I have a quick question.
Yes.
I'm going to jump in. So you talked about timing. Is what you're doing, is it amenable to memory?
Yes,
as well?
Yes, it is.
Because that for especially for machine learning and other kinds of data related tasks, memory can be the killer.
Yes,
where
absolutely.
people sometimes can be patient for time.
But the big caveat there is that usually when you use switch libraries, they don't come without trade-off. So a lot of the performance improvement you will see in runtime is at the cost of memory. So, or even some similar importance on edge devices, but also on cloud, power. So if the libraries run very fast, but consume lots of power, consume lots of memory, they may still not be applicable to you, right? But that gives you a better sense of like a more realistic requirements spec.